Okay, welcome everyone. This is the blog course from Computational Science Zurich. And in this lecture, we will be giving a tutorial, the first tutorial, in fact, of korali, which is a software for Bayesian uncertainty quantification and optimization. Let me grab my pen here, my iPad. And let's begin by making an introduction and asking the question, why use software for what you've been learning about in these more theoretical classes you've been having and you will have later on? Well, there are, first, the question that you may have been answered already is why uncertainty quantification to begin with, right? Why do we do this? And the strongest answer to this question is by way of examples. I think the applications are the stronger testaments of the power of these techniques and these tools we have at hand. Let me grab the chat again because I lost it. Good. For example, we may have measurements in a cancer patient for which he has a tumor size currently, and he has been given medicine at these points in time, right? And the observations from reality indicate that after the medicine was given, the size of the tumor seems to have decreased. So it seems like the medicine is working. So there's two questions here. How do we validate that this is in fact the case? And also how we predict the evolution of the tumor size later on, and how we and furthermore how we optimize the application of the medicine such to minimize it and reduce side effects, but also to have the best effect in reducing the tumor size. So for this application, we apply uncertainty quantification and the techniques you have seen and the software you will see in this class, and you will obtain information such as the expected evolution, the red line here, and the bands of uncertainty that you may have within a certain degree of uncertainty, and then perhaps you can optimize the number and the times in which you should apply the medicine, right? So, and this is actually a real study, and it's in fact, and with this situation we have right now with the COVID-19 virus, there's also many studies that are being applied as to estimate the evolution of the infection, of the pandemics. And all of these are predictions and uncertainty quantifications that are done with these tools, right? Also, we can ask ourselves, why optimize? And there are many, and this is more, in my view, is much more obvious. Why do we want to optimize things? A budget, for example, how do we minimize expenditure given a certain constraints or certain goals we need to achieve as to maximize the income in our company or whatever. But in terms of science, there's also in a medical here the screen has stopped. Environment, you can see, for example, you can have tools that separate cancer block. Yes, you see there? Cancerous cells from actual healthy red blood cells. And these tools consist of very small posts that by way of hydrodynamics, they tend to separate the bigger cells from the smaller ones. So we can ask ourselves, what is the best shape for them, right? We have these standard vertical posts, but perhaps the best shape for them is an inclined shape. So we can parameterize the shape of the posts and say, okay, what's the best angle or what's the best size for them, right? And in finding the best solution, in optimizing these parameters, we can have better devices for the separation of cancer cells, for example. These are two examples, but I think examples are the strongest strongest motivations or guides to understand why these techniques are important. And I'm sure you already know them. So the methodology we use is Bayesian inference. And in here, as you have seen, we have actual measurements from physical reality. It can be from experiments, for experimental data. We use a microscope, or we use any kind of tools with their own uncertainties to measure something in reality. We then create a model for this phenomena, which can be parallel code, or can be any kind of computational code or formula or mathematical formula. Then we apply assumptions. So we assume that the data we have observed can be modeled by the computational model, given some parameters for the model and the points in which we have observed the actual data here, plus some error in which we recognize that the model has simplifications or is not exact, or there may be any kind of reasons for which the model is not a perfect representation of reality. And this error follows a normal distribution with mean 0 and some kind of a sigma error there. Okay, so with these tools, with these three things, we can apply by Bayes' theorem, which I assume we already have seen in this series of lectures. So we have the posterior, what we want to know, how the parameters of the model adapt to the observations we have, is equals to the probability, the likelihood of the data given the parameters times the probability of the parameters and divided by the probability of the data. And with this is what we observed, is how likely, or how likely are the parameters of our computational model to reflect the actual reality. And if we know they are pretty much spot on, and there's not too much uncertainty, we can use it to predict scenarios that have not been seen in reality. So we can fit it new x's here. It can be in positions in space or time or any kind of thing that you want to model to have predictions about things we have not yet observed. So Bayesian inference, in my words, in the words of an engineer, is a tool that gives you evidence-based knowledge about the physical reality. Okay, this is what motivates us. So as you well know, the approach to uncertainty quantification is fully stochastic, which means that there's a loop to be followed. We have a mathematical model to which we give an initial set of parameters or guesses that may be completely wrong. We discretize or approximate the mathematical model such that a computer can run it. And then we have computer results that the computer gives us. We have the physical systems from which we have experimental measurements, the T's here. And this is the parameters were the sigma. Sorry, I don't really remember how to write this letter. So we give them for certain x's, we obtain the real data, and this is the computed given the parameters, right? And this is our parameters. And then we compare them, right? How far are we from what we have observed? And we apply uncertainty quantification methods and optimization methods also, Monte Carlo methods or TMCMC, CMA. And with these methods, we can have, after one set of guesses, a better understanding of the system and the uncertainties that the model has, right? And with this better understanding, I'm not saying the best understanding, I'm not saying the final understanding, I'm saying a better from the initial one, right? And with this improved understanding, we generate a new set of parameter guesses with which we can do the whole loop again and iteratively approach to the best knowledge we can until we define a certain convergence rate that we say, okay, I'm happy with this. Then at the end of this loop, we will have we will obtain a set of parameters that satisfy a certain bound of uncertainty, and these parameters will provide the model with the capacity of predicting or adapting to the actual observations from the physical reality. Okay, but the main takeout of this slide is that these are iterative processes, right? They are generations one after the other until we reach the goal. Questions so far? I take it you already know this to heart, but it bears repeating, right? Because this is one of the main aspects of how the software we're going to analyze works. Okay, and this illustrates what I just said. We have, for example, if you apply CMA, we employ stochastic optimization, and we have two parameters here. So it's a 2D space, and we want to find, using CMA, the global maximum, right, of this distribution, or in this case, the global minimum. And then we have the two parameters, as I said. We have the global minimum there. So there seems to be 5 local minima, but there's only one minimum, right, we want to find. So this is the misleading aspect of this function, that they have many minimum around. So we have an initial guess, which may be completely wrong. And then what happens is, with this method, we will run a set of many guesses around with the normal distribution around the initial guess. And as we gain knowledge about the actual distribution of this function, we will improve that guess, which means that we will inch closer and closer to the global minimum, but also reduce the uncertainty, or I wouldn't say uncertainty, we reduce the scope or the width of the guesses around that initial guess, because we know more about how fast, we have a better knowledge about the gradients of this function, right? So we inch closer and smaller towards the global minimum. And that's what you're going to see in this animation. I wanted to describe it first so that you're not surprised what you will see. Each black dot is one guess. And the surrounding circle, can I go back? And so you can see it again. The circle is something called the Covariance Matrix, which gives you the covariances of the parameters and how wide you will try different guesses centered on that mean. Okay, go. Good. So you can say it's huge at first, but then it inches back in, and then you center there in the actual global minimum. Okay. So what is the role of software in all of this, in UQ and optimization? Well, for once, we want to have an interface to describe statistical problems. So in the case of the cancer patient, we want to say, okay, there's this parameter, which is the times in which I can apply medication, or the number of times I should apply medication, the things that we can, and also the things that make the environment. So what's the evolution of the tumor, and how do we provide the data to the model, the current data we have from actual measurements. So there should be an interface for you to give this to a computer, and software libraries for UQ do this, tells you how to provide this information for the algorithm to feed the algorithm and get the results. Then they encapsulate the underlying statistical algorithms. So you don't have to program CMA yourself or MC yourself, because as simple or not they may be in terms of theory, I assure you they are a little bit even more complicated in terms of programming. So it's not fun, it's not easy, and you will always if you are working in a specific field, as I guess many of you are or will, you don't want to get to complicate yourself with the specifics of the algorithm. You just want to use it and get the best out of it, right? So this encapsulation lets you use them without understanding the inner works. Although after this course, you will have a much better understanding of how they work. And then they provide a way to interface it with the computational model. So if you have a simulation of blood cell flow, or a simulation of an earthquake, or a simulation of a hurricane path, and this may be a small software, it can be a library, it can be an out-of-the-box library that you bought, and there you don't have the open source code to compile. The UQ library should be able to provide you with a way to say, okay, you run this and get the results this way, you know, and take care of all the running and gathering of the data. And you don't have to bother yourself running the model yourself and then providing the data through the UQ library. This should be automatic. All right. Then, as I said, this driving the execution of the samples, each one of these guesses that you saw in CMA, and their evaluation, and then gathering the results back should be also automatic from the UQ library. Imagine if for each guess you should run the model yourself, gather results, put it in a text file, and then use that text file for all of the guesses and put it in MATLAB, and then it can be a nightmare. But if this can be automatized, that's much better. And then, of course, once you have run the thing and have the results, you want to see them in a human understandable way. It should be concise, it should be information more than data, so you should see a plot and understand it immediately what's going on and what's happening, and get the concise and timely information from those from that data. Questions so far? Good. Remember, if you need to ask a question, feel free to unmute yourself and interrupt me. So there exists plenty of UQ and optimization libraries. This is just a subset. They may not be up to date with the precise things they do. They may have improved or changed their purpose, but to the best of my knowledge to this point, this table kind of tells you what they are targeting. Some of them are specific to a kind of problem, so some of them may be specific to chemistry, and some of them are general, so you can feed them any kind of problem and they will let you give you the results. Some of them have support for parallelism, while others don't, and they don't because they don't need it, really, because the problems they are targeting, their computational models are just functions which can be computed very fast, and there's no need for parallelism. And the language that they can be fed, or the interface exposes, depends on the type of users. Some libraries assume expert users or more on the side of the computational aspect, and some others only require users to use MATLAB or Python, which are somewhat easier to use, right? There's a question I wanted to ask you all, if you may answer via chat, please. And let me see how can I phrase it. How acquainted are you with computer science, and in particular with the concept of parallelism or on distributed computing? Can you give me, say, a number like from 1 to 10? And don't be shy, just let me know it so I can get a better understanding. In the chat. 1, okay, good. 3, okay. So it's monotonically increasing now. Okay, good. So the takeout is I didn't see any 8s or 10s, right? So I better go slow on this. And in this lecture today, I will not go even at all into parallelism or more complicated stuff. Tomorrow I'll go further on that. But I know now that I should take more time to explain what this means. Okay, and this is what we gather they do, but this is an oversimplification. They do many stuff, many things, specifics, models or algorithms, and they are good in their own sense, right? But today, and in this set of lectures, we will use the Korali framework. And there are reasons for this. So Korali is a high-performance UQN optimization framework. When I say high performance, is that it's focused to be run in parallel systems. So if you have a computer that has many cores, that's something that Korali targets. If you have access to a supercomputer, say Pitt-Stained here in Switzerland, that's even better because that's what Korali specifically targets. So Korali is meant primarily to be running computational models that are very heavy. So such as simulations or that take hours to run or minutes, and not just simple functions like x squared that you can compute in nanoseconds, say. Oh, sorry, so I think the screen froze. So let me restart. There you go. Okay, you didn't miss too much, just me talking. Okay. So why do we use it in this course specifically? Well, first, we gather it's easier because although it's originally meant to run on C++, it also has a Python interface, and I take it most of you have at least are familiar with Python, and if not, you can learn it very easily. Python is very user-friendly language, and can be written or can be programmed the same way you speak. That's in my perception, right? I rather use C++, but Python makes things so much easier. It's easy to teach and learn, and this is a subjective impression, but I think you will find it the same as I do. Mainly because it's well documented, right? And then we can provide direct support. So in case everything fails, feel free, and we'll be happy to receive emails from you or messages or any kind of communication asking how we do this, how I do that. The goal is that you have a working knowledge of Korali by the end of this course that you can apply to your own problems and research, and so that is useful for you. That's the main goal. We wouldn't be and shouldn't be using this if we didn't believe it was very useful for you to have in your toolshed. Okay, so why would you use it in the future besides this? To run parallel distributed computational models, which you may find, and it's adapted to extreme scale studies, as I said. So if you're going to run this on 5,000 computers and Pitt-Stained, then you better use this because it's tailored for that and to not waste any computational power and also energy, right? And provides resilience. So if you're going to run this on thousands of core nodes and then for hours, if something bad happens, you would like to have minimal loss of progress because there's money. We're talking about very big bucks in terms of computation. So something happens, you want to recover from where you were. And also it's highly documented, open source, and if you will, you can develop your own algorithms for UQ and test them here. So if you're a statistician or you are researching stochastic methods and you want to try them, you can easily integrate them in Korali and not have any other knowledge about how Korali works, and it should work, right? Okay, so enough with the introductions. Let's begin doing stuff. Feel free to follow me, as I said, but in this hands-on tutorial, I will do these things myself and will expect you to interrupt me whenever I do something you didn't quite get, okay? So the first practice is very straightforward. And for this, I prefer to share my computer screen rather than my iPad screen. So let me see if I had a document here. I had a PDF of this lecture. Don't quite remember where it is. In downloads, sure, yes, here it is. And stop sharing this screen. And instead share this other screen. Good, I'm sharing, can you see it? Why is it not showing the chat? Please let me know you're seeing this, my screen, my computer screen.
Yes, we are.
Good, thank you. Okay, this is a practice one, and let's follow the steps. First, visit the website here, csc-lab.eth.ch, korali. You will see the front screen. You can download the code and you have all this information here. But what I want you to do is to go to the installation page and check whether your system has the necessary requirements. So we go to documentation and the installation page, and we see system requirements. You need a C++ compiler, makes sense, right? TNU make, wget, a Git client, and Python 3. And most of you will have all of this given by your system already, right? If not, make sure you install it. There's information on how to get them. But assuming we all have this, we can proceed. And then I have my computer here. Well, that's not my computer. It's a computer in our lab that I'm accessing remotely. And I will remove whatever I have here such that we can start from scratch. Tutorial out. Okay. Then let's go. First, download the latest stable code. We have a master branch, which we are developing things, but then once we say, okay, this is good enough and stable enough to publish a new version, we put it in the latest branch. And you can clone it easily by doing this. Just copy, paste, and get in the code. So I'm now currently cloning the code into my computer. Okay, done. And then it says to install Korali, just run this, right? Go to the folder. Here. Good. And then run install. But for the sake of going a little bit faster and not stalling in this step, we will add this build jobs, which creates a parallel installation, so it runs many things at a time. And let's make it fast. Am I here? Oops. Okay, so there's an error here in documentation. Okay, never mind. I'll fix that later. It's just jobs, not build jobs. Okay. So what it's going to do, if you see here, that is that there are some requirements that if you don't have them in your system, Korali will take care of. So it will download the GNU scientific library, which it needs for random number generation, and it will install it automatically. If you already have it and the correct version, which is more than 2.4, then you may choose to add this flag, not to install GSL again, and Korali will take it from your system, right? So it's currently compiling that. And while we wait for it to finish, it should take 1 minute or two, not too much more. While we wait for it to finish, First, let me know if you have any questions so far. And then I will encourage you to, well, if you have any problems, see troubleshooting. There are many things that can happen. But there's this section called Korali Basics, which is basically what I'm going to teach in this lecture. But if you forget what I said, or if you want to take a look yourself, the whole thing is documented. How to define an experiment, how to define the statistical problem, how to define the algorithm you want to use to solve that problem, and so on and so forth, right? So, and how to run it, how everything is defined here, so you can go back and take a look. Then when you're ready to run, you have a very heavy computational model, you can run it in parallel, and this is how to, description of all the ways you can do it. And then we will take a look at this tomorrow, okay? And there are tutorials, basically demonstrations of applications already done with Korali that you can take a look at. Case study, for example, no, not this, example experiments. And you have optimization, for example, you can take a look here at the description, and then you can go to the code. You would have it in your computer if you clone the Korali code, but you can take a look online here in GitHub and see what's the shape of a Korali application, like this. Okay, let's go back to our tutorial, to our practice. And the only thing we are asked to do, left to do, is run any of the basic tutorials to make sure it's working correctly. So let's do that. Let's go to tutorials. Let's go to basic, which are the simpler ones. It's just a showcase of the things you can do. Let's go to optimization, and let's make sure by running any of these examples that Korali is well installed and is running. Okay, never mind the output. The main takeout is that whatever happened, it worked fine, right? Just run correctly. This is a confirmation that we have good installation. Let's go back there. Good, any questions? Awesome. Let's go back to the iPad and continue taking a look at what we can do now. So new share, iPad. Good, we're back. All right. We finished our first practice successfully. Now let's make our first steps in developing a new experiment. In this case, we want to do some optimization, right? Let's have the simplest experiment or the simplest problem we can think of, and I can think of this one. We have a model that reflects some kind of physical reality. In this case, it's just a cone upside down in 2 dimensions, right? And we want to define a search or parameter space. You can call it however you like. So now we have the f of x and y. We want to define a search space within which we are sure, or at least we want to find a solution. Say this is a budget, or this is some kind of number that outside this parameter space we are not interested in knowing anything about the function, right? And then this is something we don't know yet, but okay, we don't wink wink, we know it because we know this function, we can plot it, but this is something we would like to find. These 3 things we would like to find. The maximum, the point of x at which the maximum can be found, the point of y at which the maximum can be found, and the value of the function where the maximum lies, right? This is 0, 0, and 5 here, right? Okay, so now we define a very simple problem. Let's use Korali to solve it. And to solve this problem, we will define an experiment. An experiment in korali has a specific meaning, which is something that holds a problem, or rather a problem description. In this case, of type optimization. So we want to optimize something. The objective function we want to optimize is described by this, as we have seen. We also describe in this experiment the parameter space, as we have seen also, and then the solver, and we might choose to use CMA or any other, right? It can be DEA, or we can use a gradient-based approach, a gradient-based method, anything you would like to use. And then when we run this, we will find the x and y that maximizes the function. This is what we want to get, the x and y at 0, and then the f at 5, right? Basically what I just described, but this is how korali sees it. Korali sees experiments in which the problem definition and the solver are defined along with the parameter space. And then you run is an action that you call. You say, korali, hey, I just defined the problem, now run it. So what's the interface to define all of these components of an experiment? Well, korali uses a special type of interface, which is called a descriptive interface, as opposed to a prescriptive interface. In the former, you define the what, so what you want to do, and not the how to do it. How is korali takes care of, right? In a prescriptive interface, you should describe the steps that need to be followed to get whatever result you want. Prescriptive interfaces are very good for many things, but not for this case, because we want to define something that can be solved by many different means. So we want to define what we want to do, not how to do it. This is how a korali application looks like. We have let's begin again. Let's start again. We have a model, which is my function, my minus x squared minus y squared plus 5, that we import, or we can have it defined in the same code, but here for the sake of size or space, I just included it as a library. Then we define a new experiment by doing this, E equals korali experiment, and then we define the problem. The problem is of type, and you will find this in documentation, so you don't worry if you don't understand exactly what's the nomenclature. An optimization of type stochastic, because we are going to use stochastic methods to solve it. And then the objective function to maximize is this one, my model, which I just included here. But again, it can put it in the code right there, and it will be the same. Then the parameter space, we give names to the variables. In this case, it's very easy. Variable 0 will be called x, and variable 1 will be called y. If you know something about Python, you will know that this is a dictionary. So this E is a dictionary which contains keys. In this case, this key is called variables. And since we're using this notation here, this key happens to be a vector, or a list, sorry, a list. And this list goes from 0 to n, where n is the number of variables. Enough Python. This should be, in spite of that, it should be understandable anyway. Okay, so we define also, because CMA requires it, a lower and upper exploration bound for the variables. So CMA will try values for these samples within the -10 and 10, for both y and x. Then we say the solver, I want to use CMA, and I want to use 8 samples per generation. So you remember all these black dots that showed in animation? Okay, those were like 30 dots per generation. These are 8 we want to use in this case. Then we instantiate the engine, which is what runs the experiment. So the experiment is kind of a static object that can be run, and then we run it using krun. This is the only specific function call that you will have in korali, run. And then you can see that this requires minimal knowledge. So this is a series of advantages that you are using this, right? It's kind of obvious. You don't need to know too much of programming. Just follow the shape of things here, copy and paste. It is the same for C++ and Python. So add semicolons to the end and you will have the C++ version of this, plus or minus a couple of things. You don't need to know how korali operates. Korali will take care of everything under the hood. So you just run this and get the results. And it's a modular approach. And what I mean with this is, say, here you have defined the problem description in the parameter space. If you want to change how you solve it, you just say here, instead of CMA, it's DEA. And we consider CMA and DEA to be two different modules that you can interchange. That's why we call it modular, because you can change things without changing the other stuff that you have defined before. Good, I think this is it. Any questions so far? Good, let's continue then. Now, the model, which I didn't specify in this previous slide, I just cheated and took it from here, should have, oops, let's go forward. The model should have a specific shape. What I mean by shape is the arguments it receives is just one. It only receives an argument called korali sample. And the korali sample is also a dictionary, which contains specific keys. For example, parameters. Parameters represent the values that the sample has been assigned for each of the variables that you have defined in the experiment. What I mean by this is that we will have in each sample a different stochastically generated value for X and Y. And the way you access X and Y is by accessing the parameters key, which is in itself a list, which contains two values, one for Y and one for X, in the order you have specified them. So 0 is for X just because you define X first, or if you're given 0 index to X, right? So each sample, as I said, is different than others, or the other 7 samples on the generation. And you can access their value like this. And then you perform the calculation. The calculation is just the function we have said, x squared plus y squared and negated plus 5. And then you save the results like this back into the sample. So the sample is both an input and an output parameter. In the sample, you store the value of your function evaluation such that CMA knows that the evaluation of sample, it takes it from here. So it's an agreement between you and the algorithm that this is the name of the key that you will assign the result to. In the documentation, every problem or every algorithm will tell you what it expects from the model, right? So you get the variables, run the actual model, and then you save the results. That's it, right? So, as I said, the samples are dictionaries. As I said, also their content depend on the problem and the solver. So, for example, with the evaluation of the function suffices for CMA, but other, for example, gradient-based methods also require that you define the gradient. So the gradient is the value of the derivative at the given point for each of the axis, right, or the variables. So for X, you should specify this should be a vector, which you say, okay, at this point, the gradient, the value of the derivative is 0 for X and 0, or I don't know, 1 for Y. In this case, yeah, that's fine, right? And the method will use this information to better approximate to the best solution, right? And then all of the problems and solvers use the same interface, so you don't need to look in the documentation to know how to create your model. You know that it's just one parameter you receive. Okay, questions?
Yeah, so I if I understand it correctly, like the interface is the same, but where you write performing calculation, this is where I write my own interface to the software that I'm using for my engineering problem.
Yes. Mm-hmm.
Cool.
So we will see how to do that more specifically. There are different types of models. Some are more close than others, and you may prefer to use one way or the other. But exactly, this is where you call something, get results, and you know how to get these results, and you provide X and Y, right?
Yeah, makes sense.
Mm-hmm. Okay, looking inside the hood of Korali, and I want you to have this information because it may give you a better understanding of later on when we talk about parallelization, how things are solved. This is the engine. This is what you didn't define. You instantiated the engine and then use it to run. And what it does is very simple. It takes the experiment you define, checks whether it has finished, because there may be experiments for which the initial state is also the last state. This is a very mathematical or very finicky thing to do, but you should start with check termination. It passes the information, necessary information, to the solver and the execution to the solver, and the solver will generate, based on the parameters you gave, new samples, a set of new samples, which are handled by the problem module. It's not, the solver doesn't give the samples directly to the computational model because there may be some pre-processing to be done by the problem. In the case of CMA, and stochastic optimization, there's basically almost nothing to do as pre-processing, but there are more complex problems that need to have some pre-chewing of the parameters. So the problem changes may change the parameters to have a better representation, and then for the model computes. So you can see here it receives the parameters and then outputs a changed set of parameters. So this is the dash here. It's changed. It may be the same, as I said. The computational model receives each one of these. In this case, one by one, it computes them sequentially because this is not parallel. And it outputs the F of the sample, so the results of running the computational model for each one of these changed samples. And there's a statistical model in the problem module that digests the results and may get the likelihood from these results, and returns either one or many, or a set of data that may or not reflect the same number of samples. This is a post-processed result. For all of these samples, you get a result that updates the state of the solver. So this may be the likelihood of the samples given the data, right? The experimental data. And the solver, with this information, updates its state. So it approaches, improves the convergence, or approaches the mean towards the maximum, all kinds of stuff. And after doing this, it stores the results back into the engine so that you can have access to these results at each generation. Excuse me. And the engine stores the results into a file or wherever you would like to store them, and then checks if the solver has finished. If not, it continues the same loop. If yes, then exits and you have your results. So this is the main driving loop, and every single problem experiment that you can define in Korali follows this this path or this logic, right? It's meant to drive iterative generation-based algorithms. Okay. So second practice, let's do this. Let's do an optimization, the optimization problem we have defined with Korali. And let me exit this screen and share with you my actual screen. Back again. So we are here now. First step, let's take it easy and go to the documentation. We'll go and do this now, but this is more for you later on when you review this lecture, that you take your time and go nice and easy and take a look at this here. It says go to module configuration, yes. Problems, model optimization, which is what we want to do, and stochastic, unconstrained. And here you will see sometimes a description. You will see a couple interesting things. First, which of the solvers we have in Korali currently, because it may be, you may add your own, address this type of problems, CMA, TEA, LM, CMA, and sequential optimization. The results you should expect from running this this problem given these solvers. In this case, you will get the best sample. So for all of the samples you run, you'll get the one with the best actually evaluation, and you get all the information you want from here. Then there are things called variable specific settings. So if you choose this problem, then the variables may need to have these properties defined. One is name. This is mandatory always, but this problem also lets you know the granularity. So if you want to define a discrete variable, you may use it by using this setting. However, there are defaults for the variable. So if you don't define it, so you can see here, I did not define that property, it will take a default, so it will not fail. But if you don't define a property that is mandatory, it will fail. And then the configuration of the problem tells you the things that you need to define for the problem to run. And the only one you need to define here is the objective function. And you should specify a computational model, right? And I do that here. So in the documentation, it tells you what you need to define and what is default. Now, the second step of this tutorial was to check the Cma solver, which we want to use. So we go to solvers, Cma. There's a description. And it tells you how to use it, of course. That's what I did here. Sorry, I went over. I use solver type Cma. It tells you you can define all of these variable specific settings, initial mean, initial standard deviation, but I chose to use the lower and upper bound. So some of these are not mandatory. If you define the lower and upper bound, you don't need to define the initial mean or standard deviation. So you should take a look and see a further look into the documentation and see what things need to be defined in the presence or absence of other parameters. We define the lower and upper bound, it suffices for Cma to run correctly. And then the configuration itself of the solver, we need to tell it how many samples per generation should it run. And this is done by population size, right? And in this case, we chose 8. Many other parameters you can adjust. These are like knobs that you can adjust and get better or worse convergence, depending on your problem, and that you can use, but also termination criteria. Termination criteria tells the solver when to stop. And there are, I believe, standard determination criteria. For each one of these is a standard. In this case, many of them are infinity because we don't want to stop by default on those. But the most common, I would say, for Cma, where was I? Termination criteria is the minimum value difference threshold, which means after 2 given generations, how much did the best result change? If it didn't change too much, then we reach conversions and it's time to finish, right? It makes sense, right? Because if you want to get the best result with a certain degree of freedom or like margin of error, you can say, okay, if it didn't change within 0.0001, then it's good enough for me. This is where you define it. But you may also define maximum generations, if I can find it here, or it's a property. Yes, maximum generations is you say, okay, I don't know how this is going to go, but don't go more than 1,000 generations, because then I would know it didn't reach convergence and I'm wasting computational time. So you may use this combination of the two of them and take a look at the other ones to better define in your case, when korali should stop computing. Okay, let's go to step 3, and we will end with this for 5 minutes. And I want you to run this command here to get the tutorial code which we'll be using in this lecture. So we go back. I just run this very fast. And here we will see the rest of the practices, practice 2, 3, 4, 5, and 6, which I want you to do. Hopefully we will do them all today, at least demonstrate pretty quickly what's going on. But I want you to later on do them yourselves and come back with questions tomorrow if you have any. Okay, so let's, instead of step 4, let's take a pause right now and come back 11, so in 5 minutes for the rest of the lecture. See you then. We're back. Okay, it's recording again. Good. So let's finish with the first. Let's finish with the first practice. Let me share the screen again. Good. So we have seen the documentation for both CMA and stochastic optimization problem. Now let's program our first application in practice 2. This is the application we had in mind. If I can make it a little bit bigger. Right there. So if you go to practice2.py, you will find the skeleton of a Python application in which you should fill here, 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 and here with the things that are missing. In this case, it's just a matter of transcribing what you saw in the slide, but it will give you a feel of how things go, I believe. This is the easiest way to start. First of all, we need to define our experiment. Let's begin with that. So in this case, it's letter by letter, word by word. We define the problem type, and we say it is an optimization stochastic problem. And then we define, please interrupt me if you see anything strange or you don't understand something, objective function. In this case, it will be, and I'm taking it from here because I have the function here, my objective function, as easy as that. And then we define the variables. First by name, and then we say, okay, the lower bound for this is -10. The upper bound, this one is +2. Basically, we copy and paste for the next one, changing the number and the name. That's it. There we define the problem type and the parameter space. Now we want to configure the solver, and we say solver type. We want to use CMA, and we want to also have a population size of 8. Looks reasonable. There's a formula if you read the CMA paper, or I don't know where it is, that tells you what's the optimal. I think it's a proof of some sort. Tells you the optimal number of samples per generation to use depending on the number of variables you have. So the more variables you have, you should specify more samples per generation, but it's a logarithmic formula, so it doesn't increase too much with every one you add. That's the main takeaway from this. And as I said, I want to define a criterion with which to stop running. And in this case, I will be just giving a simple number, max generations of 100. I can give the conversions rate, the minimum difference between two different results, but let's not go that complicated. Just say run for 100 generations and that's it. Oh, it was here, placeholder for that. Okay, and then we run. We say my engine, which is I gave the name K. You can give it any name. Please run the experiment I just defined. The only thing that is missing here is let's define the function, right? And as I said, the sample is a dictionary from which I can query parameters. So we're tackling this thing now here. 0 will be x. 1 will be y, and then we perform the function minus 5, and we save the result. F of x for this function is equals to f. I could as well copy this and place it here, but I think for the sake of understanding right now, it's nice that we have it separated, because in the future, as you have said, we will have a complex computation, or we can be calling a library of sorts, so let's keep it separated. Good, we have finished our first practice. Let's run it. So if I didn't make any mistakes, this should run for 100 generations. Here, 100 generations. And it will give us the optimum value, found at 5, as we expected. And the values of x and y will be very close to 0. So it is 0.0000. You can see here the exponential notation. So this is basically 0. We could go even further into the closer to 0 if we added more generations. Because you remember that the scope in which CMA searches reduces after each generation, so we can go further and further on. But this is basically it. So, in case you should try this by yourself, and even without the help of the slides. But in case you get stuck or you have any doubts, you have a solution. The solution is basically the same thing as I just did, with the difference that I took the time to define a more sensible termination criteria, which says if the difference between two different generations is less than this, then okay, finish. Let's see for how long does it run. Okay, it needed only 39 generations, but you can see here that the results are less precise. It's less closer than 0, so to speak. E-4 instead of E-8 where we have, but this is good enough for what we have described. And now you can get a very good impression of how things work. All right, we finished. Let's go back to the iPad. Any questions so far? Sorry, I didn't ask before. Good. Seems to be either very clear or extremely confusing. Not to warrant any questions so far. So let's continue on. How do we access the results? We have seen only one way, which is we saw it in the screen. It's printed in the screen. Okay, this is x, this is y, this is the function value. But you may not want to do this necessarily. If you want to integrate korali into a bigger application, such that that application can check the results and do other things, then you wouldn't want to gather this from the standard output, but directly from the experiment. And korali provides ways to do this. So they can print it into a screen, as we said, but this can be silenced. You can access the results directly from the experiment objects E. So just access the result directly from it because it's still a dictionary. use the plotter tool to see the entire convergence history. So this is even more data. You can see how long did it take to converge, and we will see this. Or access the actual files that are saved into the hard disk, which are JSON files, which are basically a format that is understandable, human readable, and can be shared by many different applications. And the entire history is saved there. So I guess we should take a look and follow practice 3 and see how these things can be done. So practice 3, first, let's silence the experiments console output. So we don't want to see any of this, right? So let's go back to the web page and go to module configuration experiment, because the experiment is in itself a module in Korali. And we can see that if you go down, we can see console output verbosity. If we're running Korali inside another application, we don't want Korali to be spamming things. So let's go to practice 3. We have the same, this is a solution from the previous practice, basically. And now it asks us to prevent console output. And we can see here, we can do this easily by saying experiment console output verbosity. No, sorry. There's options here. Silent, minimal, normal, or detailed. They're very self-explanatory. And if we do this and then we run, you can see that it ran, but nothing was printed to screen. And then there's something else that happens is that when you run a result folder with all the generations are saved. And if you go and take a look at each one of these, all the internal state of the solver and everything that needs to be known is saved onto this file, including the state of the random seeds, the random number generator. So whenever, if you want to restart your, we will see tomorrow, if you want to restart your experiment from a given generation, you can do it and you will get the exact same result because even the random number generators are saved. Okay, we don't even want this. We want to produce 0 output. And then what we can do is to go file output and say experiment file output enabled equals false. In Python, the false is uppercase. Okay. So now we run this and nothing is saved into the files. Now we can take this experiment and put it inside another application. So Korali is not the main driver of the application; it's the application itself running Korali inside for some particular reason. Okay. Now let's go back here, and we actually skipped step 2, but I wanted to do it in practice 2 because we have more generations. We have 100 generations there. And so it says, get the results, we got them, and print them in your application. So what it means, this step is to access the results directly. And to do this, sorry, this is meant to be done in practice 3. Sorry for the back and forth. Well, this is the step it's asking you to do. We want to print the results manually. So we want to say best x equals something, and we gather this from what you saw before in problems, stochastic. These are the results that are saved. Best result, no, results. Best sample, and this best sample will be the same thing we access in the model. So if you want to access the best x, it will be stored as parameters 0. Same with y. 1, and for the best evaluation, it would be f of x, just like that. And then we can print it here on the screen. I guess this is the syntax for this. If you don't understand the syntax, don't worry. There's a solution folder that will give you exactly what you need to know. So to make it nicer, I can say it like this. This should be it. If you're making mistakes, this should go. But I did make mistakes. So what I'm okay. There's no need to do this actually. You can see here, it prints the value yourself. You do it, you print it instead of just korali. For x equals 0, basically, and y equals 0, the best solution is 5, give or take, right? So this is pretty easy. Now let's go back to the practice, and something else we can use to visualize the results is the plotter. And the plotter is a tool we include in korali. If you follow me here and you see using korali and go to tools, one of the three we have right now is the plotter. And it tells you, it's just a command you can run. It tells you how to use it, the syntax, and what to expect. But instead of spoiling the surprise, I'll just run it here and see what we have. But since I suppressed the results, you can see here, it's complaining, hey, I didn't get the results. So let's not suppress the results, and then run again, and then actually plot it. You need to open this first. You will be able to see the evolution of CMA as it looked for the best x and y that maximizes the function. And I think this is the upper right diagram is the most informative in my view. It tells you how the best values of x and y have evolved given the generation. So it continued to go on and on. It jumped very largely between different values. And since this is a symmetric function, you can see that it goes zigzagging along. But at some point it reached the point of convergence and then stood there. And this represents what you saw in the animation, right? These other plots have to do with the internals of CMA, and they indicate the eigenvalues of the covariance matrix indicate how much it will, the width of the tries, the sigma of how distant will the guesses, the samples be with respect to the mean, the current mean, right? And this is all the stuff that perhaps we should ask George or Daniel. I'm not such an expert to know what this means. But anyway, this is something you can get the more detailed evolution of the results. And to take a the final step, well, I did it in the inverse order, but if you go to the results, you can see here for all 39 generations that we run, and this is the last one. You can open this file with MATLAB, you can open this file with Python, you can open this file with anything or any other tool that has a JSON plugin. And then you can access all the internals and also the results here. Should be somewhere around here. Well, the idea is that you don't iterate this file like this. You open it with a JSON tool, and then you can better navigate it, right? Or use it as input to other applications. Okay, this is all about outputs and results. Any questions? Good. Then let's go back to the iPad. Great. Now let's continue. Let's do something a little more complicated, which is probably probability distribution sampling. So what we want to know is, well, first I want to talk about the modules that I so many times cited, but I didn't very much talk about. There's many things you can do in korali in terms of problems and the way to solve them. That's the solvers. And this is not an exhaustive list, and it's also not a permanent or rigid list. As I said, since these are modules that can be inserted or taken out of korali without affecting the rest of korali or the rest of the modules, you should expect to see more and more. There are many currently in development. Reinforcement learning is one of them, and they will be part of korali soon, right? But in this case, in this specific example, we will choose probability sampling. And what we want to do, perhaps you have seen this animation already. We have a real distribution here, described by a function that returns a non-normalized probability distribution. So its integration from -infinity to infinity doesn't necessarily add up to 1, but it describes a probability distribution nonetheless, and we want to get the shape of it, right? And this is the parameter space. So this distribution is obeys to the probability of parameter 1 being equal to parameter 2 given the function. And what korali does in all this stochastic methods do is kind of get a fitting of all the distribution space via sampling, and then narrow down on the spaces of more density of probability, such to give more detail there. But also by virtue of having more density of samples there, it also tells you about the distribution. So as you could see in the bottom, I can repeat this. Oh, sorry. Well, I have it here. As the generations progress, first we have no idea. That's why we sample from a uniform distribution, and then we start annealing towards the best the actual distribution. The more information we get, right? So let's do this. Let's sample. Let's gather information about the shape of our probability distribution using korali. And let's go back to my screen. I'll take a few shortcuts here because it asks you to here the practice tells you, okay, to check this documentation, check this solver. Let's you can do that later. Let's go faster now and go to practice 4. In practice 4, you have a model. I should call it probability distribution rather than model, but okay. That you have a problem type sampling, which is what we want to do. You have a probability distribution defined by the model. So this returns a number. But I want to show you the model because you will see, never mind the distribution, this is just an arbitrary distribution, that it doesn't return f of x, it returns p of x, because we want the probability density at this point. All the rest is the same. Parameters p0, p1, and this is the shape of the parameters. It's in fact it is the upside down cone that we just saw. I think, yes, it is. And since it's non-normalized, we don't care about it not adding up to 1, because the solvers the samplers in korali make account for non-normalized distributions. Okay, let's go back to practice 4. And we see we use the Markov chain Monte Carlo method to sample this. A burn-in is the concept of running a set of samples first to gain a little bit of an idea first, and then actually run the sample, all the samples we want for each generation. And then we define the parameter space here. In this case, instead of defining lower and upper bound, we define initial mean and standard deviation. And these are inputs to MCMC and serve, as far as I know, to give it a better idea. If you have some idea about the distribution, you can, this is an initial guess. This is not a prior information. We'll see that later for a Bayesian problem. This is just an initial guess for MCMC to start taking a look, wandering around the distribution. In this case, since we are going to run many samples, and MCMC, each sample is a generation, so it does not do parallel or concurrent sampling as other methods do. We want to have the frequency of file output as once every 5,000, a console output once every 5,000 generations, and then we want the diversity to be detailed because we want to know everything. And this is just because, right? And something to know is that even though we can define a very large or small frequency, however you want to put it, so it prints every many generations, the last generation will always be saved or shown. So you will always get the results, even though you define a very large frequency. This is all you need to know. And I think complete the korali application in practice 4 folder. You know what? I may have mistakenly given you the solution in the problem itself. So I guess the solution has the same thing inside. Yes. Okay. If you want, I will fix this later. But if you want, just delete. Don't take a look. Just delete all the things that are filled here, and then try to do it yourself. But even this is better because I will not do it now, so we can go faster. But it says once you have done that, once you have filled all the details of your experiment, run korali and use the plotter tool to show the distribution of each variable and their covariances. You will see what this means. We run practice 4. Okay, model is not defined. Did I change the name of it? I may have. How come? I'm loading it. No, this is right. Okay, so it's wrong. There's a bug there. I'll fix it later. Don't worry. Okay, so we run for 50,000 generations, 1 sample per generation in MCMC, and we reached a solution. But since this is sampling, there's not much you can gather from this output, right? This will tell you kind of where the maximum distribution may lie, but it will not tell you all about it. To get a better idea of the distribution, you can start by plotting the results. So you run the plotter, and you will get the figure here. This is the shape that the function I passed to korali describes. And it's still an upside down cone, so to speak. And this is the probability distribution of the x variable. So how the density of the probability changes with x. This is how it changes with y in the bottom. And here in the lower left corner, it tells you their covariances. So how one changes with the other, how they are related. And you can see they are pretty much related. You can interpret this many different ways, but this is their covariance, right? And here on the upper right corner shows you every single one of the samples. It tells you where they lay, so it gives you an idea of the density of the probability. Right? It's very much correlated with this lower left. plot. Okay, questions so far? Good. So we have yet to finish the practice. It says, change the model so that not one of the variables no longer affects the distribution, and repeat step 4. Let's do that. Let's play around. So I expected you, this step is meant for you to play around and see what else can be done. So let's say that V1 no longer affects the probability. So it's completely, the probability is completely independent from this parameter. And let's run again. Now we plot again. Let's see what's the implications in terms of the distribution of what I just did. Did I break everything? Well, now you can see that the first variable still very much is correlated with the probability the distribution, but the second variable has almost no correlation. So this should be completely uniform. It is not, because you may need many more samples to represent that uniform distribution, but all in all, you can see it's pretty much linear. It doesn't matter what you choose for it, it doesn't represent the probability. Okay? So play around with this, with the probability functions, and see what crazy shapes or things can you infer from it, right? Or even better, what real life problems do you have that can be sampled and use korali for it? Right? Okay, let's go back to the iPad. We have plenty to cover still. Meanwhile, if you have any questions, let me know. Now let's do something interesting. Let's do Bayesian inference at last. And let's infer model parameters using korali. So, Bayesian inference. We need to find the model parameters that best reflect the reference data we have from experience. And we define a Bayesian inference problem in korali. There's one such model in korali called Bayesian inference. And we use the one that says by reference because we want to use reference data, that is the Y. Can I write here? This Y is a reference data we have at these given points. We want to find the best of these parameters given a certain error that is guided, that is estimated by a normal distribution. We use, instead of a function that we give korali, we will use a model, an integrated model already inside korali, which is called additive normal likelihood model. And to calculate the likelihood for each sample, it requires that you give a vector of the reference data and a vector of the points in which you observe that data, right? So these are two vectors you need to provide, either to korali or to the model. You will see exactly what I mean with this. Okay, then you have a likelihood model. The likelihood model needs to run a computational model that you provide for each one of the x's, given the sample parameters. It looks like this. My model, it's a function you have, will receive the proposed parameters in the sample given by korali, but also a set of points, all the x, that in which you have made the observations. And with this, the model should calculate for each of the x, the f of x, so the value of the computational model at those x points. Don't worry if you don't quite follow right now. This will all become clearer and clearer as we progress. Excuse me. So we define the parameter space. The parameter space describes this one. This is the parameter space. We have one variable, another variable. We can have n variables, n parameters. But also, we want to estimate the value of sigma, because sigma will tell us, this is sigma if I'm not wrong, will tell us, oh, this is epsilon. Okay, never mind the notation. I guess this is sigma. Sorry. This is sigma. This is the value we want to know. So we want to know the standard deviation of this distribution that gives us the error noted by epsilon. How big is it? The bigger sigma is in this case, the least adjusted the model is to the reality, even in presence of the best possible parameters we will find. So ideally, we want to find as certain parameters that best reflect the reality and also minimize the sigma. But sigma cannot be completely ever minimized because you have noise everywhere. You have instrument uncertainties, you have computational uncertainties, you make assumptions in your computational and mathematical model, so sigma has a lower bound that cannot be surpassed. But in any case, you want to minimize it. Okay, I hope this is clear. Each of the variables we may have as users prior information about the variables. So you may have an idea of what they from other experiments or things that have been said to us about more or less how the variables should behave, or the space in which we should explore the variables. And this is given by the prior distributions. And we should create distributions for each one of these. And then we use a solver. In this case, I would choose to use TMCMC, which is a good solver for Bayesian problems. And this is all you need to define in korali for you to do some Bayesian, some good old Bayesian inference. Okay. So let's put it into code. Here, as I said, you need to provide the excess space-time or whatever else in which you have made your observations, the value of the observations, x and d, and then the prior distributions. In korali, you create distributions by themselves. So you have distribution 0, distribution 1, distribution 2, and you describe them, say, for example, this is a univariate distribution with a uniform shape that goes from -5 to 5, sorry, -5 to 5. This other distribution is also uniform, goes from -5 to 5, and this other distribution, I want to put it in terms of a normal distribution that has mean 0 and standard deviation 2, because I chose to. I could use a uniform distribution as well. Okay. These are the distributions. And now we define the things that you're already familiar with, the variable space. We have parameter S0 follows this distribution. Parameter variable 2, S1 follows this other distribution, this one. And sigma follows this distribution. So you can see they are assigned the prior distributions by name. We believe this is the most intuitive way to do it. Instead of by number can be a little bit confusing. And if you change the orders, then you have to change all the numbers again. But if you put it by name, then the name will stay no matter where you put them. Okay. Now you configure the solver. I want to run TMCMC for 1,000 with 1,000 samples per generation. And TMCMC by default will stop when it anneals completely the actual distribution. So it has a built-in conversions criteria that I don't want to change at this point, and it's sufficient. When it says it reflects perfectly the underlying distribution, it will finish. And then the problem, I did this backwards now because I wanted you to see that it doesn't matter the order in which you put things, basically. As long as they are defined, this is not, as I said, this is not a set of instructions, this is just a description of the problem. And I want to do a Bayesian inference problem by reference, and this is the name we'll put to it. We may change it to be more, or not, to be more clear, but it's just the name we gave it. We use this additive normal instead of multiplicative normal calculation of the likelihood. Go to the to the documentation if you want to know more about what this is. And then the reference data, you can see here, sorry, this should not be it. You should be already have it there, X, right? No, sorry. This is Y. This is the reference. Let's go back. This should not, oops, this should not be it. It should be D. Korali needs you to give it, for the calculation of the likelihood, the real world observations that you have at hand. And your model, we will use a Lambda function. You may not be aware of what this is, but this is pretty much something that facilitates the description of functions that receive values through it. So just follow along, and you should not get complicated by its notation. It says basically that this function, my model, is described by an input S, which is the sample that comes from korali, but also takes X, which is the reference points of time and space where we made our measurements, just directly from this environment. So directly from what we define from this X, it goes directly here, fixed. It's always 0.3, 0.5, 0.3. This doesn't change. So this facilitates us to give it this information directly to the function, but we say S comes from korali. And I have this new slide that makes it even clearer. This is my model. This can be a red blood cell flow model or whatever. We get the reference points here. This is the X I told you about. I think this is, I put it in the wrong order, but doesn't matter. And the sample from korali. So now we get the S0 and S1 parameters. And here we don't store just one value f of x or p of x. We need to store the calculation for each one of the reference points. So for point in x, remember 0.3, 0.5, and 0.3 again. No, it's 0.2, something like that. We say that the value is some operation. We may be calling GPU-based simulator here, and we give it the xi here, and the value of my model parameters. And for each one of these values, we append a result, append it to a result vector. So this is my f of x for all x, right? And korali will take this reference information, and we calculate the likelihood of I don't remember the notation of the data given the parameters. It's a function of all the f of x's that we have. So let's call it I don't know, function, and the reference data that we have, that we got from the reality. And this function is the additive normal we set up before in configuration. Okay, but yes, question.
The value is y value we are calculating.
Yes, I think I'm using different notations in different slides. I apologize for that. Yes, that was the assumption that y is equal to f of x and the parameters plus epsilon. Oops, epsilon. And when I say d here, yes, this is d. I guess I could justify myself and escape from this situation and say that this is some kind of function and this is observations, but that would be cheating. So, and the function produced the observations for each x.
So like we are taking the output and then we are putting into firstly. In
this case, yes, we're taking the output of the computational model.
Yeah, so
and
like
putting it here.
The computational model could be anything like FEM and all these things.
Exactly, yes. Mm-hmm. And this so-called reality function is not a function, it's just reality, right? Okay, I hope I clarify more than I confused you, but this is basically the, if I could clear, okay, no. Okay, I give up. So yes, let's go and do practice 5 if we have enough time. I guess practice 6 will be for tomorrow. So I stop sharing now. Share the screen. So practice 5. It says, check the documentation for the sampling problem. No, this is, sorry, Bayesian inference problem. You find it here. So let's just do that. Let's go and say, my problem is of type Bayesian inference and likelihood by reference. And you have all the, okay, this is the additive, this is the function I said, the additive normal function with which you calculate the likelihood. And this is the sigma, this is the standard deviation which I talked about. The least it is, the better, because then you can say it's pretty well adjusted to the observations, the parameters you found and the model you have. Okay, and then we say we go to the solvers, DMCMC. Where is it? Here. Also, there's some information, and you can look at the paper that's described, and the configuration, termination criteria you can define, and default configuration here. So let's not go too in-depth in it, and just go to practice 5 folder and take a look what's in there. Here, practice 5 is pretty much, just not to make you lose too much time, it's pretty much done, except that the values are missing. So let's fill them in. And let's actually fill them in from here. So my problem type is of Bayesian by reference data. The likelihood model, I want to use additive normal. The reference data, I can just put it like this, 0.6, 0.3. And the computational model, I will have a lambda function S of my model that takes the sample itself, but let's here get reference data. I think I have it. I have them. So if you take a look at the model, yeah, okay. Get reference data. So the model here in this folder, what I have is you as a user provide this reference data and reference points, and I put them all here. So let's go back. Easily use them directly. So you can say that X get reference point, get reference data, and then I can just easily say reference data will be Y. Let's use D, and the model takes the sample and X, and that's it. The distributions, prior one, univariate, uniform from -5 to 5. Same here. Let me just prior 2. -5 to 5, and then this one, just for the sake of let's make it also a uniform.
What is the meaning of the get reference points?
Get reference points is something that, as a user, I define to get the vector of values at which the function should be evaluated, the X. Okay. But this is not something that has anything to do with korali. This is as a programmer of the model I provide. I may be taking this from a file or from, I don't know, from a web server, from anywhere. But this is not korali. You can do this like this instead, right? But for convenience, in this example, I just gave 2 functions, so you can take them from there. And I guess this was meant to be normal anyway. So in 0, standard deviation 2. Okay. Prior distributions defined. Let's define the variables S0 And the distribution of this S0, all the information I have from before is given by this distribution, S1, no, sorry, S1 given by prior 2. And this is important because sigma is very much expected for the Bayesian inference problem. So you need to use this special notation, which is between, how do you call this? Brackets? Not just sigma, but if you use brackets, this is something that you say that this is part of the likelihood model. This is not just a computational parameter. We decided to be this way, just this is the best way we found it, but we could make it explicit and say, okay, this is a computational. A statistical variable, these two are computational. Anyway, sigma distribution. Okay, then it's done. Once again, let's go back. So the model is something that is given to us by the developer, of the scientist that did the model for some phenomenon. And we go to the model, and besides the model itself, that expects a sample and the reference points, the scientist was kind enough to give us the data they observed in reality, which include the reference points, which is all the x's, so the positions in space in which they observed it, and also the reference data, which is the value of the reality of the physical reality at those points. This is given to us. This is not part of korali or anything. Then we run it. Practice 5. Something I made a mistake. Okay. Yes, the same mistake as before. I will fix that later. So basically, I don't know.
Is the variable like we are getting the reference point, which are the variable or something?
Let's go to the model then and answer your question. Say again.
I'm asking like the get reference point.
Yes.
Given like what like prior or something else.
So these reference points don't have anything to do with the variables we define in korali. The variables are the parameters of the computational model. So say we say that the red blood cell stretches more or less depending on these parameters, okay? But it can be the viscosity of the red blood cell. These are the variables that we define in korali. The reference points is, for example, different points in time in which we observed in reality. So at t equals 2 seconds, the red blood cell in the physical reality in observations in the microscope showed 3.2, a width of 3.2. So it was this long. At second 3, we observed that the cell was 4.9 centimeters or nanometers. So these reference points and reference data have to do with reality. And the parameters that we define in korali have to do with the configuration of the model. So the knobs you can turn back and forth, high or low, to adjust the model to reflect better the reality.
Okay.
Okay, I hope that responds to your question. I made a mistake, so it's model, not my model. Strange, because I ran it yesterday. From model, yes, okay. Because I just wrote it. Okay. Let's run it, and this will be the last thing we do today. In 7 generations, TMCMC finished, and we want to see what else we wanted to do with this. We want to use the plotter tool and see how this looks like. And we can see, this is showing us that the most likely value of S0 and S1, and S0 in this case is this between 0.8, something like that, and S1, 2.1. Around these values is the most likely values for them that best adjust reality, the observations, the reference points and reference data. And the sigma, the distribution, is around here. Well, I should have used a uniform because negative sigma doesn't make any sense, but it's symmetric. It tells us more or less how well adjusted we are. And this should be 1.13, depends on the model and what you're trying to do. May tell you that you're very well adjusted, so the model very well reflects reality or not. Okay. And the last thing I want to do is to use CMA, not to sample the posterior distribution of the variables, but to find just the best sample, the one the best adjusted. If you want to use these values for a next process or something else, I want to find that. And it's as easy as, I have it in solution, so I don't want to program it now. Oh, I don't have it. Okay, let's do it tomorrow then. Basically, what I wanted to show you is to observe, to get the best, of all the samples we run, the best one, if you want to use it for practical purposes and then run something else based on that. Okay, let's finish here. If you have any questions, let's start tomorrow with a Q&A, short Q&A, and gather all the questions you may have. Try to do these exercises up to exercise 5, and let me know what came out of it. Okay, see you tomorrow then.
Thank you.
Thank you.